A stratified fluid is a fluid with density variations from one point to another. This is a stratified fluid system. A lighter fluid on top and a slightly heavier fluid below. The density changes abruptly at the interface. The curve of density against height looks like this. This kind of stratification occurs, for instance, where warm water lies above cold water, or fresh water above salt water. An abrupt density change also occurs at the interface between air and water. Both air and water are fluids, and together they may be thought of as a stratified fluid system. Often, however, the density doesn't change abruptly, but instead varies continuously. The ocean and the atmosphere are usually continuously stratified. These density variations profoundly affect the motion of the water and air. Airflow over mountains is one example, as we see in these time-lapse photographs of cloud motions. Smog is another example of the effects of stratification, and there are many other examples in science and technology. In this film, we will use laboratory demonstrations to illustrate the basic phenomena in stratified fluids. We will emphasize fluid systems in which the density is greater near the bottom. That is, the density decreases with height. When such a system is disturbed, gravity waves result. Gravity and friction eventually restore undisturbed conditions. The system is stable. If the density increases with height, however, the fluid tends to be unstable. The fluid near the bottom of this tank is being strongly heated. It becomes lighter than the fluid just above, creating an unstable situation. But let's get back to the behavior of fluids that are stably stratified in the vertical. We will concentrate on flows over obstacles. These reveal most of the fundamental phenomena that occur in stratified fluids. Moreover, such flows frequently occur in nature. We will begin with the simplest example, the flow of water over a barrier in a channel. We will produce flow relative to the obstacle by moving the obstacle through the water. When the camera moves with the model, we see an apparent flow from the left over a stationary model. In this way, we produce an approach flow uniform with height. Phenomena in water flows depend on the dimensions of the obstacle relative to the depth and on the approach Froude number. A local Froude number may be defined at any section as the ratio of the fluid velocity at that section to the square root of the gravitational acceleration times the local fluid depth. Since the square root of GH is the speed of the fastest small amplitude water wave, the Froude number compares the fluid speed to wave speed. Where the Froude number is less than 1, the flow is called subcritical. Where it is greater than 1, supercritical. Let us now look at flow patterns as we increase the Froude number based on the approach conditions from low to high values. First, a very low approach Froude number. The flow is subcritical everywhere. The free surface dips down slightly over the obstacle. Next, we increase the approach Froude number to a higher subcritical value. The obstacle is at rest. As it starts, notice a blocking effect, which causes a rise in the upstream level. When the motion becomes established, the upstream subcritical flow near the obstacle draws down as it passes over the barrier, becoming supercritical in the lee. This supercritical flow in the lee changes abruptly to subcritical flow downstream as the fluid passes through a hydraulic jump. Here's a hydraulic jump at the base of a dam. Next, an approach fluid number somewhat greater than 1. Now we get an upstream hydraulic jump. The fluid goes from supercritical far upstream to subcritical as it passes through the jump, then passes to the supercritical conditions downstream as it passes over the obstacle crest. Finally, an approach fluid number much greater than 1. The fluid swells symmetrically over the obstacle, and conditions are supercritical everywhere. Here's the development of this supercritical flow pattern from an initial state of rest. Since the fluid number is much greater than 1, the fluid speed everywhere exceeds the speed of the fastest waves, and all disturbances are swept downstream. Let's look again at these flow patterns as the approach fluid number is increased from low to high values. A slight dip down over the obstacle. Hydraulic jump in the lee. Hydraulic jump upstream. Symmetric swell over the obstacle. These supercritical and subcritical channel flows are analogous to supersonic and subsonic flow of gases. The fluid number corresponds to the Mach number, and the hydraulic jump corresponds to the shock wave. Phenomena similar to those of water flows in a channel occur in stratified liquids with internal density variations. These waves are at the interface of two liquids with a slight density difference. The oscillations are slower than those on a water-air interface. The frequency sigma of the waves is proportional to the square root of the restoring force in both cases. The restoring force for water waves is the gravitational force G, but for internal waves, the restoring force is G multiplied by the small number delta rho over rho bar, where delta rho is the density difference between the liquids, and rho bar is the average density. The quantity delta rho over rho bar G is sometimes called modified gravity. Of course, even in the water wave case, the G in the formula for the wave frequency should be multiplied by delta rho over rho bar. But here, delta rho over rho bar is very close to 1. With respect to the flow of two fluids over obstacles, the important fluid number is now the internal fluid number of the approach flow, in which G is replaced by modified gravity. A critical value of this number, as in water flows, corresponds to a fluid speed equal to the speed of long waves. But the critical value is no longer 1, since the wave speed also depends on the ratio of the depth of the lower fluid to the total depth. For two fluids, the flow patterns are determined by the internal fluid number, the ratio of the depths, and by the height and length of the obstacle relative to the depth. Now we will vary these parameters and see how the flow patterns change. A long obstacle and a low value of the internal fluid number of the approach flow leads to subcritical flow at every section and a slight drawdown of the interface over the barrier. This long, gently shaped barrier minimizes vertical accelerations of the fluid, and the pressure remains nearly hydrostatic. That is, the pressure is related directly to the depth. However, for the same ratio of fluid depths and the same internal fluid number, a shorter model of the same height results in weak lee waves, as non-hydrostatic pressures become important. As we increase the fluid number by increasing the speed, these lee waves become stronger. At a still higher fluid number, the waves show signs of breaking, as in the undular hydraulic jump on a water surface. Further increase in fluid number would result only in a lengthening of these waves. Now let's increase the size of the obstacle. A strong hydraulic jump occurs downstream. The upstream subcritical flow changes to supercritical as it passes over the barrier. Further downstream, it jumps to a new level, and the flow again becomes subcritical. Look upstream as this flow begins. Notice the strong blocking effect. That is, the lower fluid ahead of the obstacle builds up in depth. As in water, if the approach fluid number is high enough, the flow is supercritical everywhere. So far, phenomena at the interface have resembled those we saw on a water surface. This is because we have had a deep upper fluid in all cases. Let's remove some of the upper fluid. The lower fluid is now deeper than the upper. Downstream of the obstacle, the depth of the lower fluid abruptly decreases in what might be called a hydraulic drop. A common feature of all the two-fluid experiments we have seen is that the liquid air surface remains quite undisturbed despite very large disturbances at the interface. We can explain this if we forget for a moment that there are two fluids in the channel, and notice that in all of these two-fluid experiments, the ordinary fluid number is much less than 1. In other words, conditions are very much subcritical as far as disturbances of the liquid-air interface are concerned. The free surface becomes disturbed if we move the obstacle sufficiently fast to obtain an ordinary fluid number of the order 1. In such cases, the internal density variations are no longer important. We can also disturb a two-layer system by moving an obstacle in the upper layer. There is an interesting application of this. It was noticed long ago that ocean-going vessels off the coast of Norway suddenly found themselves unable to maintain their accustomed speed as they moved past the mouth of a fjord. This deadwater phenomenon was first explained by the Swedish oceanographer Ekman. He pointed out that the fresh water from the fjords flows out in a density current over the heavier water of the ocean and forms a two-layer stratified fluid system. At certain speeds, a vessel can create large disturbances at the fluid interface. These disturbances contain a great deal of energy, and the power of the ship's engines is used up in creating them. Notice that the liquid air surface is rather undisturbed. The wave drag comes principally from the internal waves. If the ship is moving at a high speed, the interfacial disturbances are much weaker, and the deadwater phenomenon no longer exists. A basic feature of two-fluid systems is that the fundamental mode of oscillation is a simple sine wave at the interface. A three-layer system, however, has two distinct modes. Here's one, and the other. Indeed, one mode is added for each layer. Carried to the limit, an infinite number of infinitely thin layers has an infinity of modes. This is equivalent to a fluid system in which the density varies continuously with height, as in the atmosphere and oceans. Before we see experimental examples, let's consider the parameters which govern the flow of a continuously stratified fluid over an obstacle. Again, the most important non-dimensional number is the internal fluid number. Here, delta rho over rho bar is the fractional density difference from the top to the bottom of the channel. The flow patterns are influenced not only by the internal fluid number, but also by the relative dimensions of the obstacle. Now we will look at some experiments in which we vary the internal fluid number and the obstacle height. Our experimental fluid is a saline solution in which the salt concentration, and therefore the density, decreases continuously with height. The tracer particles are neutrally buoyant polystyrene beads. the uneven distribution of beads does not reflect the density distribution. The density distribution depends only on the salt concentration and is more or less linear with height. Here is something analogous to the supercritical flow of water. The Froude number is high, and the fluid simply swells over the barrier as water does at supercritical speeds. If we drop the internal Froude number below its first critical value of 1 over pi, simple sine waves appear in the Lie. These internal waves are not possible in a homogeneous fluid. To see how they can arise in a stratified fluid, let's look at the vorticity equation for a frictionless, non-homogeneous fluid. Omega is the vector vorticity, v is the velocity, and p is the pressure. d omega dt is the rate of increase of vorticity of a moving parcel of fluid. The last term shows that the vorticity can be generated through the interaction of the pressure and density fields. This equation can be solved under certain circumstances to yield flow patterns corresponding to the experiments we have just seen. Here's the pattern for the first of these. We can make use of this pattern to show the relationship between the generation of vorticity and the wave motion. The density varies from point to point in the fluid, but because the motion is steady, the density is constant along a given streamline. The density gradient is everywhere normal to the streamlines. Despite the motion, the pressure field is practically undisturbed, so that the constant pressure surfaces are nearly hard. As the fluid descends in the lee of the obstacle, this gives a vorticity generation, or fluid rotation, in this sense. This rotation permits the descending fluid to turn upward toward its original level. On the way up, vorticity of the opposite sense is generated. The fluid can now turn back into the next phase of the wave. Of course, these waves can also be explained from a buoyancy force viewpoint. The descending fluid particle finds itself in a heavier environment and is forced back up as it moves along. It overshoots, then descends again, and so on. When the barrier is small, the waves have small amplitudes, as we have seen. If we increase the height of the barrier, keeping the internal Froude number the same, the amplitude of the waves gets much larger. We are speeding up the action photographically in this and some later experiments to bring out certain features of the flow more clearly. In the theoretical flow pattern corresponding to this experiment, closed streamlines appear. In the experiment, these regions appear to be unstable and break into turbulent eddies. The loss of energy in this turbulence causes the wave amplitude downstream to be less than that indicated by the corresponding theory. In this experiment, we raised the height of the model, but kept the Froude number the same. A decrease of Froude number reduces the length scale of the fluid motion, and in addition, the wave structure is no longer a simple sine wave. When the Froude number is low, but the obstacle is large, the flow pattern again has a small scale, but is of a very different character. The approach flow consists of a number of jets moving rapidly toward the obstacle, sandwiched between layers of fluid that are stagnant with respect to the obstacle. In these flows, there is always a stagnation layer extending from the bottom of the channel to the level of the crest. At low Froude numbers, the fluid doesn't have enough kinetic energy to move up over the obstacle from this region. This illustrates the tendency of a slowly moving parcel of stratified fluid to maintain its original level. The jets and stagnation layers further up in the fluid are not so easily explained. To see how a jet develops, we'll watch the establishment of a flow with a single jet at a higher internal Froude number. Watch the region above the obstacle near the top surface. The fluid stagnates there. Then the stagnation region begins to spread upstream, ultimately forming a layer of fluid at rest with respect to the barrier. At the same time, we have a stagnation layer near the bottom ahead of the obstacle. Between these two is a single jet. As we start the model from rest, notice how the lower stagnation develops. Jet phenomena are common in geophysical fluid systems. Examples are the Gulf Stream and the equatorial undercurrent in the oceans and the jet stream in the atmosphere. Another example of a natural flow of a stratified fluid is the flow of air over a mountain ridge. Such flows have been carefully studied in the Owens Valley east of the Sierra Nevadas in California. Here is a streamline pattern constructed from balloon and glider observations there on a day when there was a strong lee wave. The vertical scale is exaggerated in this cross-section. We can model this flow in the laboratory. This is a model of the Owens Valley region. The density stratification of the atmosphere is simulated by the density variation in salt water. The Froude number is the same as that in the atmosphere on the day the observations were made. A single large wave appears over the valley. When the wind is weaker, the number of waves over the valley increases. When the flow in the model is adjusted downward to give a corresponding Froude number, the same three waves appear in the experiment. Density stratification has an important effect on diffusion in fluids. For example, smoke coming from a chimney diffuses turbulently if the atmosphere is not stably stratified, as we see in these speeded up pictures. When the lower air is stable, as in the morning or the early evening, the smoke comes out and flattens into a long, thin layer. Strong stratifications, or inversions as they are sometimes called, confine contaminants to the lower layers of the atmosphere and cause many of our air pollution problems. Here's another example of the effect of stratification on diffusion. The salt water in this tank has a gradual density decrease with height. The effluent is a bit lighter than the water at the level of the pipe and rises and spreads out at an intermediate level. This effect has an obvious application to the disposal of sewage and other wastes in the oceans. In summary, we have shown that stratification gives rise to forces that generate internal waves, inhibit turbulent diffusion, and create strong velocity gradients in jets. These are the basic phenomena in stratified fluids.